Okay, so the last time basically we had started the topic of motion segmentation. Basically, we were discussing utilizing motion for separating moving objects from a static background. So we have basically we have a so we should have a background model which will be constantly updated, because the background in real life scenario, backgrounds may get changed due to either illumination changes or any background motions, or there are a number of reasons that we discussed last time that can lead to change in the background scenario. So we need to have some kind of a model of the background which will give us the estimated background at time instant t, and then we take the current image frame or video frame at time instant t and subtract the two, the estimate this. So this is, let us say, the estimated background frame. At time t, and this is the current frame. So then after subtracting the two, we will get to know where are the changes that has happened. So if those objects which are in moving, so the difference image will be thresholded. So that means we need to decide a particular value beyond which we will consider there is a significant change or not. So any value less than that may not be considered as a significant change. So only those locations where there has been a significant change, which is greater than a particular threshold value, those will be registered as foreground regions, and all other regions will be understood to be the part of the background. And in the last class, basically, we saw three methods for estimating our background. One is just simple frame differencing. Where basically our background is simply the image at time instant t-1 or t-k, some previous time image frame. And then we saw we could actually mean image, where the background is basically a mean of image from past or mean image, or I'm skipping the xy parameters. I'm just using the t notation here to indicate the function of time. So basically we take an average over past n frames, and then that gives a background model which is slightly better than the frame differencing method. And still improvement was, if you, instead of mean, if you take actually a median image as a reference image. So median basically introduces less distortion as compared to mean. So those three methods were very simplistic methods, and they could be done fast. Frame differencing was very fast. In mean and median, we need to do some computation and some memory buffering. But those requirements could also be easily taken care of if we do a running average if you update our mean image or median image by doing a running average approximation, then you don't need to store all the past n frames, and also the computation also is less. But there was one disadvantage which could be a major problem. First of all, this threshold value has to be set manually by experimentation. And another problem was this was a global threshold value. That means this threshold, we cannot set threshold value separately for different regions. So we would basically use that threshold value for the entire image, for all the pixels, for all the pixel locations in the entire image. And thirdly, this threshold would not get updated over time. As the background is getting updated, the threshold itself may not get updated, because every now and then a human will not intervene and try to see whether the threshold is working fine or not, and keep on updating the threshold. So there has to be some mechanism by which the threshold should also get updated over a function of time. If background is getting updated, it makes sense to update threshold also, because right threshold value is very important. If you choose a threshold too low, we may miss many of the regions which are real candidate for foreground regions. And if we keep a threshold too high, if we keep a threshold too low, we may get a lot of noise regions, a lot of background regions also as a part of our foreground regions. And if we keep threshold too high, we may miss some of the objects in the foreground, or we may miss some of the part of the objects itself. So the objects may get if we have a high threshold. So we had seen different images for that, different examples of that. So now we will see some methods by which we can overcome this problem of threshold, static threshold and a global threshold. So one method, which is a simple method, basically, it tries to basically model our background using a Gaussian distribution. So it tries to model our background, assuming that the distribution is Gaussian. So what is done here is that, in fact, this approach was used in a paper, first paper, where they were trying to basically detect pedestrians in a video, street video. The idea is simple. For every pixel, so in this image, for example, for every pixel location, basically you try to model the intensities of that pixel over time as a normal distribution or as a Gaussian distribution. So using the past n frames over time, you use the intensity values that have been observed for that pixel over past n frames, and use those observations to fit a Gaussian PDF. Fitting a Gaussian PDF basically means just finding out its mean and variance, because a Gaussian normal distribution can be characterized just by these two parameters, its mean and variance. So for every pixel, we'll have a different Gaussian distribution, because every pixel, so treating every pixel value as a random variable and using the observed values of that variable over time, and finding out the mean and variance to come up with this Gaussian PDF. Now to update our background over time, we just need to update the mean and the variance. So as we said, the background needs to be constantly updated. So to update our background, we will just need to keep on updating the mean and variance of our Gaussian distribution. And the way it can be done very easily is, again, to avoid any computation or memory requirement, storage requirement, basically we'll update our PDF by doing a running average method. So the equation for the running for updating our mean and variance at time t plus 1, that is the next frame, and for the next frame is shown here. So the updated mean value will basically be a function of the previous mean value. That means the mean value observed till time t and the current frame value at time t. So this f, I think it should have been better represented as I, because we have been using the notation I. So this is basically the current time, the value of the pixel in video frame at time t, at time instant t. That is the current observation, and this is basically the mean observed till now, because mu t will be the update, will be basically the mean of the distribution that has been observed till time instant t using the past n frames, or using the past history. So this is basically our history, and this is our current observation. Okay, and we will use a factor alpha. Maybe let me write. Alpha will basically be the factor, or that I can call it rate of updation. The rate at which you want to update our background model. If this alpha will be from 0 to 1, so the value of alpha will be from 0 to 1. Meaning, so if alpha is high, if alpha is close to, let us say, if alpha is 0.9, then the new mean will be mostly dominated by the current observation. The percentage of the current observation will be of 90%, and the percentage of the history, of the past history, will be only 0.1%. Whereas if we keep alpha as, let us say, 0.1, then our mean, the new mean, will be mostly dominated by our past mean, that is the past history, and the effect of our current observation will be very less. It will be only 10%. So how quickly you want our background to update to new observation, you can adjust this by adjusting this value of alpha. If you want to rely more on the current observation and not on the past history, then you can keep the rate of updation alpha as high. Whereas if you don't want to so quickly update, because that may be reason why you don't want to so quickly update, because the new changes may be just due to noise. If there is some change happening, it may be just due to some noise or some random motion, and you don't want to quickly adopt our background model to any random motion. So in that case, you should give less weightage to the new observation and should give more weightage to the past history. So what has been observed consistently over past n frames, you can give more weightage to that. So it is basically, it's alpha is just a parameter by which you can adjust that how quickly you want to update your mean. Similarly, same in the analogous way, you can update variance also with the alpha as our tuning as a factor for rate of updation, and this is the variance till time t, the history, and this is the new variance, variance that you observed using the current observation. So in that way, basically, you can keep on updating our mean and variance after every frame. So how do you how do you use this model then? So you need to first initialize in the beginning when you start your processing your video frame. For the first frame itself, you can use the mean as the current value at time instant 0. The mean can be simply that current intensity value, the first intensity value that is observed, and the variance at time instant t can be approximated by taking a small window around that pixel and calculating variance in that small region, X and Y. So for every pixel, take a small window around that pixel and find out what is the variance in that region, and just use that as an approximation for our variance over time. And once we initialize it, then we basically use our this updation method, this running updation method, to keep on getting our new mean and new variance over time. Now, how do you decide whether a particular pixel region is a part of the foreground or a part of the background? That you can classify using this simple classification heuristic. What it basically says, if you have got, so using our current mean and current variance, you can try to see how far the current observation is from the mean of the Gaussian. So the idea here is, for example, let us say if this is your Gaussian, and this normally our normal Gaussian is centered around mean, and it is statistically can be shown that 68% of our observations will fall within one standard deviation. So within mu plus sigma and mu minus sigma, almost 68% of our observation will fall within one standard deviation. And if you want to incorporate 95% of our observation, then you can go up to 2 sigma. And if you want to incorporate up to 99.7% of our observations, we can go up to 3 standard deviation from the mean. So let us say you think for your current scenario, you think that 60% of our time we will have a background. We'll observe our background, and the moving objects of the foreground part will cover any region only, let us say 30 or 40 or maybe. So accordingly, we can select this k value. So basically, what we are doing is IT minus mu t greater than k sigma t. So if k is 1, k can be 1, k can be 2, k can be 3, k can be some 2, whatever. So you can select, this just k value. So you want to be, only be conservative. So you can select k as just 1. So anything which is beyond 1 sigma of standard deviation, you consider all this as foreground distribution, and only this part remains your background distribution. So why this will be a background distribution? Because this observation is most frequent. The probability of this observation is more frequent. So background is which is going to be observed more often, and the foreground, as I said, foreground is that part which is in flux, which is transient. So those will be observed less frequently. So this part will be of both foreground part, and this part will be this part will be a background, and this part will be a foreground part. So any pixel value which is beyond 1 sigma or 2 sigma, whatever k value is set, that can be set as a part of the foreground. That can be classified as foreground, and other part which is less than that will be considered as part of the background. So the thing is, our threshold is basically our threshold now. Our threshold is now nothing but a function of the variance of our Gaussian. And this variance is getting updated over time. As our background is getting updated, as our Gaussian distribution is getting updated, this threshold is also getting updated. It is no more a static value. And moreover, this threshold is also different for different pixel, because for every pixel we are modeling a separate PDF. Every pixel is being modeled as a separate Gaussian distribution. So sigma t for each pixel will be different. So this threshold is no more a global threshold. For it is a custom threshold for every pixel. So it is, so that means for different region now can have different threshold values, and this threshold value will also keep on updating over time as our situation, as our scenario is changing, as our background is getting updated, our threshold value will also get updated. Any question till this point? So it has overcome the major problem that we had in our simple thing. It still does not cope with multimodal background. What is multimodal background basically? So there may be some reasons because of which a background distribution itself may not be just, it may not be possible to model a pixel background pixel value just using one Gaussian. For example, in this scenario, this probably a scenario where probably there is an overhead cloud motion. So within short period of time, cloud is covering and uncovering probably the sun. So the illumination is changing very rapidly and repetitively. So when cloud comes, probably the intensity region comes this, and when cloud slowly uncovers, the intensity becomes bright. So, and this may happen in a repetitive fashion. Again, another part of the cloud may come, and again the intensity region may come to this point, and then so this kind of, now this particular intensity during this point of time, the distribution can be modeled by this kind of a Gaussian, whereas these two can be Gaussian modeled by other Gaussians. It is not possible to model all these three by a single Gaussian. It will not be a useful modeling. If you try to model all these highly different distribution by just using one Gaussian, probably it would be meaningless. It would not give a good performance, to not give a good output. So, but if you model them by separate Gaussians, that's why the method that we are going to discuss is called Gaussian mixture model. Basically, we will, in this model, rather than modeling every pixel by just using one Gaussian, we will try to keep a mixture of Gaussians. Another scenario where this may be useful, this may be needed. For example, here I think it's a water body where due to the movement of the waves or the waves of the water body, there may be flickering, the intensity distribution may be changing. So this is a plot of the intensity distribution for one particular pixel location. You can see over time there is clearly two different intensity values that are two different set of distributions which can be observed. Another scenario is probably this distribution is from the monitor screen, because monitor screen also flickers, and that also we can see there are different distribution patterns. So it's not uncommon to find multiple distributions for scenario in a real life. So this is a more advanced method where you can actually, even if your background is not a simple, not just a unimodal distribution, Gaussian distribution, mixture of Gaussian distribution, then you can go for this technique, which basically tries to model our distribution patterns using a mixture of number of Gaussians. So as I said earlier, when we were discussing segmentation by clustering, we said there is apart from k-means, there is also a Gaussian mixture model for doing clustering. But at that time, we didn't discuss detail because I deferred it to this point of time. So I'm going to discuss the details of Gaussian mixture modeling. Of course, this application in this scenario is slightly different than the way it is applied for segmentation. but it will give you the overall idea. So in this mixture model, GMM, this in short form, it is sometimes called GMM. Sometimes it is also called emoji mixture of Gaussian. So there are different abbreviations that are used to refer this technique. Okay, so we want to model the. So the idea here is basically we try to model the history of our pixel distribution using a weighted combination of K adaptive Gaussians. So the meaning of these terms will become clear. So as I said, we are no more going to rely on just one Gaussian distribution. But rather we will use multiple Gaussians K. The value of K can be 2, 3 or even more, doesn't matter, but normally 3 or 4 is more than sufficient. You don't encounter more than 2 or 3 types of distributions for a particular background pattern. So so basically we will use K normal distributions. N stand for a normal, that is Gaussian distribution, which is characterized by its mean and variance. So this sigma basically here denotes is a notation for the variance of the normal distribution. X is the random variable for that the pixel value observed at for the particular pixel value at location X. X comma Y, basically we should have two dimension, but just for simplicity we are representing it by one random variable, and we will give a weight for each Gaussian. For each Gaussian from 1 to K, we'll associate a weight. It will be a weighted combination. Why we want to give weights? Because as for example in K means, we saw that K means was biased towards clustering into equal size distribution. So but sometimes different distributions may have different weights. They may not be equal. So that can be basically modeled by assigning this additional parameter, which is basically a weight of that particular distribution. So how frequent a particular distribution is observed? If a particular distribution is observed more frequently, we'll give it a higher weight. If a particular distribution is observed less frequently, we'll reduce its weight. The sum of all the weights for all Gaussians should be equal to 1. So we will normalize the weights so that the sum of all the weights is equal to 1. And that in that sense, each weight value will also be less than between 0 to 1. So it may be if you are using K as 3, weight can be 0.2, 0.3, and 0.5. So in that way, the weights can keep on getting adjusted. So this will be a weight of 0.5 indicates a more frequent observation or distribution, and weight of 0.2 will indicate less frequent distribution. Now, how do you learn these parameters? So in the previous method, we know how to update mean and variance for a single Gaussian, but now we have multiple Gaussians, and now we have additional parameter, which is the weight of a Gaussian associated with each Gaussian. So we have 3 parameters for K Gaussians. So we need to have a method by which we can keep on updating these parameters over time, because our background has to update with time. So the first question that we need to understand, how can we learn these parameters or update these parameters of our background model? So this is our background model. This entire mixture of Gaussian is be our model by which we will represent our background. In fact, we'll see this will also represent our foreground also. We'll talk about that. So this is the second part. Actually, this mixture of Gaussians that we are going to use, they will model both foreground as well as the background. Meaning, some of the Gaussian distribution may correspond to the foreground distribution, and some of them may correspond to the background distribution. So instead of in the earlier case, we were basically within one single distribution, we were trying to separate out regions for foreground and the background. Here, we'll assume that out of this mixture of Gaussians, one or two or some of them will correspond to our foreground distribution and some of them will correspond to our background distribution. So the second question, in that case, the second question will be how to decide which of the distributions will correspond to our foreground and which one of them will correspond to our background. Because finally, our aim is to classify which pixel is a foreground and which pixel is a background pixel. So we need to answer this question: how we will distinguish which distribution corresponds to foreground and which one corresponds to the background distribution. So we are going to see these to answer for these two questions in the next few slides. So first actually there is a method called expectation maximization method. Maximization algorithm. Which is called EM algorithm, which is generally used to update or learn our mixture of Gaussian parameters of our mixture of Gaussians, but it is little compute intensive. So an alternative is done rather than using just like we were doing running average updation for our previous models. Similarly, for this K-Gaussian mixture model also, we do an online K-means approximation method to update the Gaussians. Rather than using this more elaborate and complicated method, we actually go for a simpler method, which is basically kind of an approximation of a K-means method. And it can be done in an online manner. What it basically says, it's simple. If we observe a new pixel value at time instant, let us say t+1, we try to match this value with our different Gaussians that we have been modeling. So what do you mean by matching to one of these Gaussians? We try to see whether this particular intensity value, where it is lying. So let us say this particular intensity value is somewhere here. So if it is within 2.5 sigma or 2 sigma of a mean of a particular Gaussian, ith Gaussian, we say that it is this particular value x at xt+1 is probably matching to this particular distribution, not to this one. So in that way, we basically try to compare its with the mean of each Gaussian and see whether the difference is within 2 sigma of which of the Gaussian. So if it so whichever Gaussian it matches, generally we actually keep an ordering and we match in that particular order. We'll discuss about that order in the next slide. But once we do this matching, then basically we update. We know, okay, this particular new observation belongs to this distribution. So we'll only update the mean and variance of this distribution and we'll leave the mean and variance of these other distributions. We'll not touch the mean and variance of these distributions because as per our observation, this new observation belongs to this distribution. So we'll only update the mean and variance of this distribution. How do we update the mean and variance of this distribution? We use the same running average method. So instead of alpha here, we have used a different notation because these slides are taken from another source. So instead of alpha, we are saying as rho, but it's the same. If you see, it's the same equation using the past mean and the current observation. And alpha is the rate of change, rate of updation. Similarly, mean and the variance is also getting updated in a similar way. So alpha is the learning rate here. Okay, so here they're saying rho is basically a function of alpha times the normal distribution. So it basically takes account into the Gaussian also for doing that, but that is not so consequential here. It's some alpha factor basically, and I think the equations are familiar. Only the notations is changed, but the equations are same. So we basically update the new variance and the new means of this particular distribution, which match to the current observation. And we'll also weight the, so we have updated the mean and the variance, but we have third parameter, which is the weight. So we need to update the weights also. So the weights of Gaussians are adjusted as follows. So for the one, so the idea basically is, let us say new observation has matched to this this particular distribution, then we will increase the weight of this distribution and will reduce the weight of the other distributions, because we said the weight will indicate how frequent that distribution has been observed. So if a particular observation has been observed once more, we'll increase the weight of that distribution and will reduce the weight of other distributions, because remember our weights are normalized. The sum of the weight for all Gaussians is equal to 1. So if you are increasing the weight for one particular distribution, then we have to reduce the weight for the other distribution in order to sum it to 1. So the way we do it is this equation shows that. So for the ith distribution for which there was a match, for the matching distribution where there was a match, we will increase its weight by a factor of alpha. So this was the match. Wherever for the particular distribution for where it has matched, this value will be 1. For others, it will be 0. So only for the match distribution, there will be a addition of weight by factor of alpha. And for all others, this part will be 0. For all others, the weight will get reduced by a factor of 1 minus alpha. Alpha will be some non-zero value, as we said, will be the learning rate. So all others, all other weights will get reduced by a factor of 1 minus alpha, because we are increasing one of the Gaussian by a factor of alpha. So that means the total 1 minus alpha has to be reduced from the remaining weights. And that we distribute it. So we basically reduce each weight by a factor of 1 minus alpha. So in overall, there will be the total sum will remain 1. So I hope this is clear for everyone. So this is the way, this is how we are learning or updating our model. We are updating our mean, variance, and weight for each Gaussian in this way. And this is done, mind you, this is done for every pixel separately. So every pixel we have a mixture of Gaussian. For another pixel we have another set of Gaussian. For another pixel we have another set of Gaussian. Another set of mixture of Gaussians. Let me open the video also. So as we said, the mean and variance for the unmatched distributions remains same. Only the weights for the unmatched distribution will reduce. The weights for the unmatched distributions will reduce, but the mean and variance for the unmatched distributions will remain the same. Now, it may happen that the particular pixel value at time t plus 1 did not match any of the k distributions. It may belong to a totally new object which was not observed. It can be part of the foreground region. A new object comes into the picture. So it may happen that this pixel, this intensity value may not match with any of the distributions that we were modeling. In that case, what is done basically, we discard one of the distribution. We discard the least probable distribution. So in this case, so this is the distribution which is maximum weight, and probably this one is the distribution with the least weight. So we will get rid of this distribution from our mixture, because we can only keep maximum k distributions in our model. So we'll kick out this distribution, and we'll introduce a new distribution with the current value as its mean value, and its variance will be initialized to initially a high value, high variance, and a low weight. So this is in green we are showing the new distribution that has been introduced. So probably so the mean of the new intensity value was probably somewhere here. Probably this did not match to either this. So we have introduced a new Gaussian distribution with its mean at this location and a very high variance and a very low weight, a very small weight. Why high variance and small weight? Because it may be just a random noise. Maybe a new intensity value may have been observed just because of random noise. So initially we do not give it, we don't have a lot of confidence to it. So we'll give it a low weight and high variance. Now, if this observation keeps on getting observed again and again, then slowly its variance will reduce and its weight will increase because we are keeping on updating. And slowly this distribution will gain weight and other distributions will reduce weight. And its variance will also reduce. Now, so that was how we were updating our background model. So now once we know how to update our background model, we need to classify which one is our background and which part of the pixel or which part of our which pixel will be our foreground pixel. So to estimate that, we'll use a simple heuristic. The statement that I'm stating here is that the Gaussians with the most supporting evidence means high weight, large weight, and least variance should correspond to the background. So there are two things that I've stated here, that the Gaussian which have a high weight and which have a low variance, that should correspond to background, and vice versa. Any distribution which has low weight and high variance should correspond to foreground. So anyone in the audience, can you answer why? I've already spoken about it. Why? Just to see whether you are attentive. Why a background distribution will have a high weight and low variance? So what we will do, we'll take the ratio of weight by sigma, because we need high weight and low sigma. So we'll take this value, the ratio of weight by sigma. So whichever has this value high, we'll consider those as background, and whichever has this value low, we'll consider those as foreground. So we'll do a sorting. So for each k Gaussian, we'll get its this value of ratio of weight by sigma, and we'll sort it. So we'll sort this value. So some of the mixture will have low value, some of them will have high, some of the distribution will have high values. So as we said, towards the high we'll have background distribution, and towards the low end we'll have the foreground. So how do we decide which one is foreground, which one? So we need to have some thresholding here. So on this sigma on this value, we need to decide a threshold. So beyond this, we'll say all those distributions which are higher than that, those will be background, and whichever are less than that, those will be probably part of the foreground model. So that is being shown here. So basically we arrange this W by sigma, and then we pick up the first B distribution from the higher side. We pick up the first. So let us say if we arrange, and after that we got the value, let us say 0.5, 0.3, 0.1, 0.1. Let us say we are having 4 Gaussians in our model, and let us say we had the weights in this ratio. Of course, we will take weight by sigma also, but let us say while deciding the background model, we only take into account the weight values. So from the top, basically we choose a threshold. As so the threshold is basically decided based on what is the minimum portion of the background which is expected to be part of the background. So let us say in a given scenario, we expect that 50% of the image region will be part of the background and 50% may be foreground. If the objects are very few, if there are only 1 or 2 people or vehicles moving, then we expect only 25% of the image region to be maybe part of the foreground, and 75% remaining 75% to be part of the background. So accordingly, we can set T as 0.5 or 0.75 and whatever. So if we set, let us say T as 0.5, then probably only this thing will be considered as background, and all these things will be considered as foreground. If we set T as 0.8, let us say, then these first two first two distributions will be considered as background distribution, and the bottom two will be considered as the foreground distribution. So this is little problematic. This again, here we have to heuristically set our threshold value. This is some thing which is a drawback. But as we said, it is not so much. It won't be so much sensitive to this, because we are already updating our things everywhere. This is a less sensitive parameter, but it is still a heuristic. It has to be set heuristically. So that is one disadvantage with this. So the thing is that what we were discussing is being shown by illustration here. So here we have a 5 Gaussian mixtures, KS5 here, 1, 2, 3, 4, and 5. So the ones which are shown in red, these are basically part of the background, and the blacks will be considered as part of the foreground, because we can see the weights of these are less, and the weights of these, as not only the weight, even the variance of this is high, as the variance of this is less, as well as the weight of these are less, because these have been observed more frequently and repetitively with the same value. So they are more tight distributions, so they will have less variance and more weight. And the foreground, which is coming and going, probably they will have large variance and less weights. So these two will be considered as our part of the foreground. And so any pixel which will match to these distributions. If the current pixel value match to one of these distributions, it will be classified as foreground pixel. Whereas if the current pixel value match to one of these background distributions, then that pixel will be labeled as a background pixel. So what are the advantages of this method? It is adaptive method, so it has all the advantage of adaptive Gaussian method that we discussed. But now we are also able to cope with multimodal background distributions. So the problems that we saw, if there is a repetitive motion in the background, either due to overhead cloud movement or due to flicker in the screen or movement in the water body, due to waves, the water bodies are reflecting, so there is specular reflection and all that. So this kind of method is found to perform well in those scenarios. It is able to recognize all those as part of the background distribution, and it doesn't classify them as foreground, whereas the other previous models failed in those scenarios. But still, it cannot deal with sudden drastic changes, because it needs some time to update the parameters. So if there is a sudden drastic illumination changes, it won't be able to cope up with that. And again, initialization is important. How do you initialize the mu, k, mu, sigma, and weights of each of all k Gaussians? You need to do it some intelligently. So one method is you can use one of the previous methods to do that thing. So you run the either median filtering algorithm or that to intelligently set these weights, initialize these weights, and then let the mixture model update them. And again, there is alpha. There are other parameters, alpha, t, and all that. So there are many parameters, and they all have to be selected judicially. Otherwise, it may end up giving bad output. So these are some problems. So if you remember the test video that we have shown earlier, so this is the background model that our mixture model learns. So you see, initially it did not adopt so well, but slowly it learns the background. So this is a part of the background. If there is a sudden change, it takes time to update our model. So if something enters quickly, immediately, let me show the results. So I'm not sure whether this is the right result. This is what I got from the internet. So this is the foreground that has been classified using our mixture Gaussian model. It doesn't show so much improvement over the previous methods. As you can see, if there is sudden changes, it fails at that point of time. Again, see, there are some problems here. It doesn't at least this demo doesn't show so much improvement over the previous methods. And partly the reason is because this scenario is not illustrative of those scenarios for which the Gaussian mixture model is meant for. It is meant for gradual, as I said, gradual repetitive motion in the background due to overhead cloud motion or some specular reflections in this that has been coming or something like that. So we find those scenarios are not here, so it's not expected. So sometimes for simpler scenario or for scenario where those types of things are not possible, it may be better to use the previous methods like median filtering or even the single Gaussian updation. You go for mixture of Gaussian model only for a complicated scenario where you want to basically, there is a long-term scene change. So for example, this is the summary that I want to basically. So these methods, frame differencing, median and mean filtering, they were pretty fast, and they would work for a simple scenario very well, where there is not multimodal background and so on. But if you want to keep on updating our threshold, as well as if there are multimodal backgrounds, if there are long-term scene changes, and if there are repetitive motions, then you can go for adaptive mixture Gaussian mixture model. Because it is shown to handle those things better. And furthermore, we can, if you want even better output, then we need to have methods by which we can incorporate temporal information. So till now, we have not incorporated a lot of temporal information. For example, we have incorporated some past history, but the sense here, it basically implies the sense in the way tracking actually uses the past history. So basically, when we track objects, we track its past history, how it is moving, with what speed it is moving, and how it is appearing. So we have, in that case, we take into account its appearance, its motion, its speed of movement, and using all that prior information, basically, if we incorporate all that information, then that helps us for better detection and better tracking of moving objects. So we'll see that in our next topic, how to, we'll discuss tracking in slight detail, not in too much detail. We'll just introduce from a high level perspective what is tracking is all about. And we'll see by incorporating tracking in our discussion, we can actually take care of some problems which cannot be handled by simple background, by these background subtraction methods. And again, we can combine some other techniques. So as we said, to intelligently initialize our parameters of the Gaussian mixture model, we can use one of these mean and median filtering method to basically initialize it well, and in that way get some better performance. But as I said, it's very hard to get the perfect output because the changes in real life scenarios are very dynamic, and that's why tracking is always followed by simple detection, and tracking helps to overcome some of the problems that you cannot overcome in simple background subtraction, and that will be the focus of our next topic. So I think we have already spent an hour, more than an hour now.